This is a course of lectures on the foundations of measurement. I'm Patrick Suppes. On my left is Duncan Luce, and on my right is Amos Tversky. The three of us will give the lectures in this course. The lectures are based on the treatise Foundations of Measurement that the three of us have written with David Krantz. Not precisely, but in a general way, there will be a correlation between the lectures and the chapters of the treatise. The three of us have divided this introductory lecture into 5 parts. First, I'll begin discussing the foundations of measurement, what it is and what it is not. Second, I want to have something to say about the structural viewpoint and what we mean by a representation theorem. Third, Amos will discuss the prerequisites for the course, what an ordinary student might be expected to have as background. Fourth, Duncan will have something in more detail than we said thus far to say about the sequence of lectures themselves. Finally, the three of us together will discuss the relevance of the course to the various sciences and the kind of applications that the theory of measurement has. Let me begin then with this first part. What is the foundations of measurement? There are a number of salient points that should be made about foundations. I've tried to list them here. First, foundations looks at qualitative structures that are ordinarily thought of as empirical structures. We'll have an example in a moment. The observations, the empirical observations, are qualitative observations, and the point of the theory is to establish an isomorphism between a qualitative structure and a numerical structure. Measurement has been established when that isomorphism has been established. Another characteristic feature of the foundations of measurement, or fundamental measurement, is that ordinarily no prior measurements are assumed. In much laboratory work and in much measurement made in the ordinary world, a variety of other measurements are assumed. It's a characteristic of the foundations to start from the qualitative observations and assume no prior measurements are available. Let's take an example that I shall only sketch. The framework of this example will be talked about very extensively in a later lecture. A classical and important case of fundamental measurement is the measurement of mass. In particular, the measurement of mass using an equal arm balance, which I've sketched here in a very simple way. Suppose we have two objects, A and B. We put A in one pan of the balance, we put B in the other, and we find that the balance stays in horizontal equilibrium. Then we'll say that A is equivalent in mass to B. If now we add a third object, C, to the pan of the balance in which A is, we observe that A and C together are heavier than B. We then have the qualitative observation that A combined with C, combined in the sense of being on the same pan of the balance, is heavier than B. And we write that combination by this operation O. So in this fundamental measurement of mass, what qualitative kind of structure and qualitative observations do we have? Well, we can see 3 things here. We have this relation of being equivalent, we have this relation of being strictly heavier than, and we have this operation of combination, which is empirically interpreted in terms of putting the two objects on the same pan of the balance at the same time. And so we want to impose a structure on these two relations and on this operation so that we have an isomorphism into the real numbers. I put isomorphism in quotes for a reason I'll explain in a moment. Now, what we want to preserve the structure and to have the same structure as we get a numerical representation is a function phi mapping the set of objects, cap A, into the real numbers. And in terms of the two relations I've written here, we want phi to have the property that phi of A, that is the number assigned to A, interpretation, the mass of A, phi of A is equal to phi of B if and only if A is an equivalent in mass to B. Secondly, in terms of this relation, phi of A plus phi of C is greater than phi of B if and only if A combined with C is, in terms of the qualitative observation on the balance, greater than B. Now, I put isomorphism in quotes up here because really, as we shall explain later, we have a homomorphism, a many-one relation. Many-one because distinct objects can be assigned the same mass. The study of such qualitative structures, of which this classic example is a prominent instance, is a main feature of the foundations of measurement. The theory of measurement, conceived in a broad way, consists of many additional disciplines, aspects, techniques, etc. It's important to say what this course and what the foundations of measurement is not. First, this course and the subject of foundations, that is generally conceived, is not a study of experimental techniques. Experimental techniques of measurement are an important aspect of a large number of sciences. For example, the literature on the measurement of the velocity of light in physics has Lord knows how many papers devoted to it and how many experiments. We shall not be talking about such detailed experimental techniques. Secondly, there is a very large and important literature on the statistical treatment of measurements. There is a literature that goes all the way back to the 18th century and involves such important figures in the history of mathematics and science as Gauss and Laplace on how observations of measurements of the same phenomena should be combined so as to get a reliable, statistically reliable measure. Again, we shall not treat of that very large topic, important in all kinds of applications. Finally, in the social and behavioral sciences, there has been a great deal of effort devoted in this century to scaling methods. And broadly, what comes under scaling methods will not be a topic that we shall discuss in detail in these lectures. Now, the second topic that I wanted to discuss in this introductory lecture is to say something about the structural viewpoint that will be a dominant theme of the course. I want to give some examples in a more explicit way than I have thus far of the concepts of isomorphism and of a representation theorem. Let's take a very simple example to illustrate the concept of isomorphism in an explicit way. What I've done is to consider binary relation structures. Such a structure consists of a non-empty set A and a binary relation R on A. So I have an explicit definition here. Let A and A prime be non-empty sets, and let R and R prime be binary relations. Then the binary relation structure German A, which is the couple A-R, is isomorphic to the binary relation structure A prime if and only if the following conditions are satisfied. There is a function f such that the domain of f is the set A, the range of f is the set A prime. Secondly, the function f is a 1-1 function. And third, and this is the structural condition of the definition, for any two elements A and B in the set A are B, if and only if f of A R prime f of B. That is, A and B stand in the relation R if and only if their images f of A and f of B stand in the relation R prime. Notice that it is the sameness of structure reflected in this equivalence. That is the central idea of isomorphism. And of course, in the theory of measurement, we use this general idea of isomorphism to establish such a sameness of structure between qualitative empirical observations, the structure of those observations, and numerical structures. It is that isomorphism, or sameness of structure, that permits us then to apply to the observations all of the computational techniques that already exist for the numerical structures. And it is why, given that possibility of numerical computation and the application of mathematics in general, it is why the theory of measurement occupies a fundamental part in the structure of science. The next idea that we use in a intense way repeatedly is the concept of a representation theorem. And again, I want to explain that concept of a representation theorem in a general way, and then say how we use it in the particular applications that are so important in the foundations of measurement. First, let's take any theory T, and we'll talk about models of that theory. We mean just structures that satisfy the axioms of the theory. So a theory T is said to be categorical if and only if any two models of T are isomorphic. That is, if and only if any two structures that satisfy the axioms of T are isomorphic. In that sense, the notion of categorical means there is just really, in an essential sense, one structure for that theory. Example of categorical theory would be the real numbers in ordinary conception. Now, in measurement, it's characteristic that we don't have categorical theories, just as we don't expect theories in physics. For example, ordinary theory of mechanics is set up to study different systems of mechanics, 2 bodies, 3 bodies, bodies under different forces, etc. We would not expect the theory of mechanics to be categorical. In the same way, we don't expect measurement theories to be categorical. The question then arises for theories in a general way, not simply in the theory of measurement. If they are not categorical, how do we want to think about the structure of models of the theory? And the general answer is in terms of a representation theorem. We try to identify some distinguished subset of models of the theory, some subset of models or of structures that have some important characteristic. And then we want to prove a representation theorem of the following sort: that every model of the theory is isomorphic to a member of this distinguished subset. The representation theorem means if I pick any arbitrary structure that satisfies the axiom of the theory, I can find in this distinguished subset another structure that is isomorphic to the first one. Now notice how this fundamental concept of a representation theorem is used in the foundations of measurement. From what I've already said, it should be clear what we have in mind as the distinguished subset R in the case of measurement. We have in mind a subset of numerical models. And what we want to prove is, putting it very intuitively, that if we now take any qualitative empirical structure satisfying the axioms of our theory T of measurement, the representation theorem shows us and proves for us that any such qualitative empirical structure will be isomorphic to a numerical structure, a member of this distinguished subset that is fundamental in the theory of measurement. Accompanying the representation theorem for a theory of measurement is also the important uniqueness theorem. It is natural to ask, especially in the case of measurement, how unique is the representation? Let's consider some classical and simple examples. In the case of mass, for example, the fundamental measurement of mass is unique up to choice of a unit. We can use as the unit a gram, a pound, an ounce, etc. There is nothing in nature that tells us what that choice of unit should be. But once we've chosen the unit, then the representation is unique. Ordinary probability is absolutely unique. We have no freedom in the choice of a unit or of any other aspect of the measurement. On the other hand, in the case of ordinary temperature, Celsius or Fahrenheit, we have not only the choice of a unit, but also the choice of a 0 point. So, for example, Celsius and Fahrenheit measurements of temperature differ not only in the choice of a unit, but also in the choice of a 0. In the case of utility, the ordinary measurement of utility or value is like the measurement of ordinary temperature. We have a choice of unit available and also a choice of the 0 point. For a given representation theorem, we then expect to prove in every case a uniqueness theorem as to how unique a representation is. It is important, however, to emphasize a second and related point about the representation. The particular representation theorem that is proved, and the particular kind of representation, is not the only kind of representation. The uniqueness theorem is relative to a particular choice of representation, and it's important to recognize that for a given theory of measurement, we can represent it numerically in more than one way in terms of fundamental operations and relations. We shall go into this in more detail in later lectures, but just take the simple case of the measurement of mass I talked about before. What I talked about was the additive representation, so that we represent the operation O as numerical addition. This is the way we ordinarily think about the representation numerically of measurements of mass. But as far as the theory goes, we could think of it in a multiplicative way, so that we represent the operation of combination not by numerical addition, but by numerical multiplication, by multiplication of numbers. And of course, as we would then expect, when we change the character of the numerical representation, we will change the uniqueness theorem, so that the additive representation of mass leads to the kind of representation and uniqueness theorem already discussed. When we change to a multiplicative representation, we would get a different uniqueness theorem. One final point about these fundamental representation and uniqueness theorems that we shall be emphasizing in the course of lectures. They have a close relation to classical theorems of a similar sort in geometry. For each kind of geometry, we can prove, or hope to be able to prove, or think we should be able to prove, a representation theorem and a uniqueness theorem. Later, we shall discuss a number of such examples in geometry. But to tie into this classical tradition in geometry, what we are doing in measurement, let us just consider the case of Euclidean geometry. The classical representation theorem is, in essence, the one established by Descartes. The representation of the Euclidean plane or Euclidean three-space by Cartesian coordinates. And the uniqueness of that representation, a way of talking about it in geometry is that the uniqueness is that up to the group of Euclidean motions. And that means it's unique up to what? To rotation of the orientation of the Cartesian axes, reflections from left to right of those axes, translation of the axes in terms of changing the origin, and change in the unit of scale. So that in the case of Euclidean geometry, just as in the case of measurement of mass or other cases of fundamental measurement, we have a representation theorem and a uniqueness theorem. And it's an important part of the classical program in geometry to establish for each major part of geometry such a representation theorem and such a uniqueness theorem. In that sense, the traditions in the theory of measurement are very close to these classical geometrical traditions of analysis.
These lectures, like the volume on which they are based, is designed to be intelligible for students with a modest mathematical background. The student should certainly be familiar with the notion of axiom, proofs, relations, sets, and the like that could be found in many elementary texts, such as those on finite mathematics. This material is necessary, but much more mathematics is used in these lectures. Generally speaking, the treatment of qualitative structures is very much in the spirit of the foundations of geometry or abstract algebra, and familiarity with this work would be helpful. The actual construction of numbers uses the properties of the real numbers, and knowledge of analysis will be useful here. For specific lectures, such as those involving geometry or probability, some familiarity with these subjects will be needed. But a student with a serious interest in measurement should be able to benefit from these lectures with a modest amount of mathematical sophistication if he or she are willing to learn some mathematics along the way.
The initial series of lectures, including this one, total 19 in number. It is anticipated that some additional ones will be added to the series over the years. But at the present time, we have 18 substantive lectures, and I will simply indicate what they are and a very slight indication of the subject matter. The first major lecture is on ordinal measurement. Suppes will be presenting that, and it concerns the conditions under which a simple ordering relation can be represented numerically when there is no other structure than order. Then I will be presenting 2 lectures on extensive measurement. That is the theory of which mass measurement is a special case, where you have a concatenation operation and you represent it additively. The first lecture will be concerned with the theory in which it is assumed that the operation is a closed operation in the sense that it's defined for every pair of elements. And the second lecture will be concerned with the more realistic model, and one that is useful for other purposes, in which the operation is not defined for every pair of elements, but only for certain pairs. These lectures, all 3 of these, are prerequisite for anything else in the series. Following that is a lecture on qualitative probability and its representation in the usual fashion with an additive probability measure. It's in structure very similar to the partial operation in extensive measurement, and in fact the proof will draw on that theory. Suppes will be giving that lecture. Then we turn to the subject of conjoint measurement, which is the study of systems that have an ordering of factorial structure, where there are two or more variables, underlying variables, that together influence the attribute that is being observed by the qualitative ordering. In the first of these lectures, which I will be giving, the case of two factors having an additive representation, where the order is preserved by a function that rests, it's the sum of two functions, one for the first component and one for the second component, and it is simply additive in nature. The second lecture, which I will also give on conjoint measurement, is again concerned with the additive case, but with three factors or more, and also with the special case of for n equal 2, when the raw information is already provided in numerical form but not necessarily in additive form, and the question is, given that numerical information, can it be transformed into an additive representation or not? The third lecture on conjoint measurement, which Tversky will present, concerns finite structures. Up until now, all of the structures that we will have been talking about are inherently infinite and have certain solvability properties. However, one can develop a theory for the finite case, and that will be described. And then he will go on to discuss representations other than the additive one. However, they're all representations of a particular character, namely polynomials. Following that, Professor Suppes will be presenting a lecture on subjective expected utility. The material is concerned with the representation of gambles, and it is asking about the existence of representations in which there is a probability measure associated with the chance events underlying the gambles, a utility measure associated with the outcomes, and that the ordering is represented by the expected utility. This lecture requires material from the first two lectures on conjoint measurement. A topic of some philosophic interest in the theory of measurement is that of meaningfulness, which I will be presenting, and it's devoted to the question of what kinds of statements, both in the numerical representation and in the original qualitative structure, can be said to be meaningful or not. This has applications both to the question of what statistical statements are reasonable to make vis-a-vis particular measurement structures, and also it arises in connection with dimensional analysis. I will be presenting a lecture on non-additive concatenation. This is the same underlying structure as in extensive measurement, that is a binary operation. However, the interest here is in the case where the representation is not additive but nonetheless is numeric in character. In essence, what is involved here is the same axioms as in the theory of extensive measurement with a partial operation, except one is omitted, namely the associativity of the operation. And that destroys the possibility of additive representations, but opens up a whole family of additional possible representations. Then there will be followed a sequence of 2 lectures on the subject of dimensional analysis, which I will be presenting. The first of them is simply a presentation of what dimensional analysis is as traditionally presented. This is the subject that is concerned with the structure, the interlocking structure of physical scales that is reflected in the units of physics. The fact that the units are all products of powers of other units. You can pick a base set of units and the others are all products of powers of them, and you can use the information that is embodied in that structure to limit very appreciably the nature of physical laws. And it's a study of that limitation and how you apply that to particular problems. And the second lecture is concerned with an attempt to give a qualitative account of where this has come from, both where the interlocking structure has come from, what qualitative properties of the measurement scales underlie that structure, and secondly, what is the qualitative equivalent to the important notion of dimensional invariance that arises in the classical theory. These lectures draw both on the lecture on non-additive concatenation and on extensive measurement and on the first 2 lectures of conjoint measurement. There will then be a series of 2 lectures on geometry that are going to be given by Suppes. One of these is concerned with the classical geometric representations, and the other is concerned with axiomatic definitions of geometries and their representations in the structures defined in the first lecture. Tversky will then treat the subject of proximity, which is the study of measurement that arises from not ordering relations but similarity relations, where one attempts to embed that information or map that qualitative information of similarity or proximity of objects and to represent that in a geometric space such that the ordering of the similarity judgments, that the pair AB is at least as similar as BC, gets represented in some fashion as a relation between distances in the geometry. Suppes will then provide a pair of lectures on the subject of axiomatizability. All of this work that we've been talking about rests very heavily on axiom systems, and there's a very considerable philosophical literature on the nature of axiomatizability, and these lectures will outline some of the material from that literature that is relevant to the theory of measurement. And finally, Professor Tversky will present material on probability models that are closely related to the measurement models. Until this point, all of the models that we've talked about have had as their basic primitive a binary relation of some sort defined on a set of elements, and it is that binary relation, the kind of notion of greater than, that is being reflected numerically. Here we shift to the point of view that what one may really observe is not a binary relation, but rather a probability that a judgment is made that A is larger than B, and attempts to provide a representation that captures the inherent probabilistic nature of the observations. We may later produce some additional lectures on various topics, but at the present time, these are the ones that will be definitely provided in the series.
The final topic we want to discuss in this introductory lecture is the relevance of measurement to the various sciences and the kind of applications that have been of importance. in the past and may be anticipated to be important in the future. The history of measurement, as we've indicated by certain suggestive remarks already, is very old. Perhaps the way to think about it in its beginnings is in close relation to geometry. We can look upon much of ancient Greek geometry as a theory of measurement. There are very nice examples of even some of the very particular and in a certain sense modern topics that we'll be discussing in Greek mathematics. For example, Archimedes' treatise on the equilibrium of planes can be regarded as providing the first axiomatic formulation of part of the theory of conjoint measurement. There he's studying the case of static equilibrium, when you have a balance with unequal arms and unequal weights, and writing down the axioms for when you have equilibrium. The modern theory of measurement began really in the 19th century. Perhaps the person to mention as of first importance historically, apart from the geometric tradition. We're assuming that geometric tradition in the background. But the person to mention first is perhaps Helmholtz, who wrote the first papers providing a qualitative theory of the measurement of mass in the way that we've talked about here and will be talking about extensively in the lectures on extensive measurement. A next important paper providing applications to the theory of mass was 1901 by the German mathematician Otto Holder. Now, these papers of Helmholtz and Holder were thought of as contributing to the foundations of physics. The early history of measurement is related, as you might expect, to physics. Discussions of the measurement of length, the measurement of mass, and the measurement of other quantities that are of importance in physics. There is more than we'll say in these lectures, a complicated and intricate history of the relation between the theory of measurement and important fundamental questions in physics. What I want to emphasize simply in these general remarks is the close connection between physics and the theory of measurement. Now, I think that Amos will tell us something about the relations of the theory of measurement to the social and behavioral sciences.
There is an interesting difference here, that although the study of the foundations of measurement in physics dates to the 19th century, is quite recent, measurement in physics has been established much earlier, and there was not much question about the fact that quantities such as mass or lengths and the like could be measured well and precisely. That was not the case in the social sciences.
Yeah, I think that's, an important and fundamental distinction. In a certain sense, there wasn't the kind of controversy historically. In the case of the measurement of mass, people wanted an analysis, but there wasn't really a question, could it be done in some sense?
That's right. And it is because of that the foundational issues about measurement are so, in some sense, more important and central to theoretical analysis in the social than in the physical sciences. Now, around the 20s, in this century, there have been a long debate centered around the personality of Campbell about the issues to whether certain attributes, such as social scientists are interested in, could be measured at all, and much of that tend to lead to a rather negative conclusion that some attributes cannot be measured at all.
I think we should mention here that the Campbell you refer to is Norman Campbell, who was a British experimental physicist. He wrote two important books, one about 1921 called Physics, the Elements, and a second book on the foundations of measurement about 1926, 1927. And he 28 perhaps. And he had this, as you're saying, negative conclusions about the possibility of measurement in psychology.
Since we're talking about Campbell, the heart of the argument, there have been several, but the heart of the argument was that since we do not have, with most attributes of concern to the social science, we don't have a natural concatenation operation, such as a placing of two objects jointly on a pen balance, and we cannot have extensive measurement, we cannot have measurement at all. And it seems to me that on that background, add to that a lot of discussion in the economic literature about the possibility of measuring utility, the meaning of decreasing marginal utility and measuring welfare. The problem about what could be measured, whether it could be measured, and what is the meaning of measurement are absolutely problem of central concern to the theory in social science. And while the work on the foundation of measurement, which started really later in the 40s, 50s and later, did not resolve all these issues, I believe that it is not unfair to say that have clarified many of the fundamental questions and put some of them as squarely as empirical question, others as sharply mathematical question, and others more philosophical or conceptual questions. So it seems to me that the major contribution of work on the foundation of measurement in the social science is really clarifying the status of those fundamental issues.
I think it's worth adding, however, that some of the developments in the social sciences aspect of measurement that have, I think, altered the view of very many people from that of Campbell, who said that it wasn't possible, to at least the possibility of measurement occurring. Some of those developments feed back in our understanding of physical measurement. One of the curious things about the history is that there was this careful development of extensive measurement where you had a concatenation operation, and there, however, was very little by way of axiomatic development of an understanding of the interconnection between measurement scales that exists in physics and that I mentioned in connection with the remarks on dimensional analysis, and that is key to the method of dimensional analysis, namely that there are a number of scales that are related to each other by being products of powers. Take an example, that kinetic energy is 1/2 mass velocity squared. That's a very typical classical relationship among three scales in physics. And that structure, which is a conjoint structure by our current language, was never really axiomatized by the philosophers of physics. And it was not until the 1960s, in work that centered in economics and psychology, that this began to be clearly understood. And then, having gained that understanding, we were able to go back and provide a rather deeper understanding of what is involved in a subject such as dimensional analysis.
So the point here is that may be worth iterating. Pat Suppes mentioned earlier, when he discussed what foundation of measurement is and is not, that it's not a method for practical. We don't teach in these courses how actually to measure things, but it seems to me that we do want to mention that a lot of the question concerning the meaning of scale, the whole notion of scale types, what kind of transformation are admissible, what one could and could not sensibly do with the scale of measurement once constructed, are issues that are addressed in these lectures.
I think really what's happened and is important in this recent foundations of measurement that you mentioned, Duncan, and some of the topics that Amos just mentioned, is that these various strands coming from physics and especially from the history of geometry, and more recently now from the social and behavioral sciences, we have a unified conceptual way of looking at them. I mean, it's characteristic of that earlier work that in Campbell there's no discussion, and in fact I'm not sure Campbell was really aware in a detailed way of all the work in geometry. For example, he certainly couldn't have said some of the things he said about extensive measurement as the only kind of measurement if he'd had any detailed understanding of the best work in the last part of the 19th century and the earlier part of the 20th century on the foundations of geometry. And I think what has happened in the last 2 decades is a much better and much deeper unified view of the subject. And it's always been a part of the foundations of physics, going, as I said earlier, all the way back to Archimedes. It's certainly been a part of the foundations of geometry and an integral part of geometry back at least to Eudoxus.
But it's really only in these last couple of decades that we've had the unified view of it that we now have. Anything else that we want to say in closing this introductory lecture?
Well, I think that one might say one more thing, and that has to do with the mathematics that is involved. One of the aspects of the work in the last 20 years has been to make reasonably clear what are the fundamental mathematical results from which all of the other measurement results derive. I think there's been progress on that front. I also think that as more mathematicians develop an interest in the field, one can hope that there will develop better and more unified proof methods than we currently have, and that the theorems will become increasingly more powerful in the future.
Amos, do you have any final comments?
Yes, well, it seems to me that when we talk about foundations of measurement, there are really different examples of foundational work in mathematics, like the work on foundation of probability or foundation of geometry. And it seems to me the foundations of measurement is really like the former in the sense that it has a lot of implications about the way you actually do and think about measurement. So there is a great deal of feedback from work on foundation on the actual practice, unlike many other fields of mathematics in which the foundation is to a large extent divorced from the actual conduct of the discipline. And I think the example we discussed of meaningfulness, of scale type, of what could and could not be measured are all examples in which foundational type research has important implication to the way the fields proceed.
Yeah, I think that's a useful and important point. The foundations of measurement, I think, in that respect, is closer to the foundations of statistics than the foundations of mathematics is to ordinary mathematical work. It has rather direct line of connection to actual work of measurement. And we hope that those of you who follow this course of lectures and who are students of the various sciences will see those connections as you follow the detailed lectures, but also that you will see ways to improve those connections and to deepen them.